Today we will talk about exercise 5.40, pendulum and peg. So this question is about this pivot here, and attached to it is a pendulum of length L. And the question didn't give us a mass, so let's just say the mass of this sphere is just m. And this pendulum swings down, and on the way down there, it hits a peg. And the peg's at a distance d from this pivot. And let's draw the pendulum here. Just imagine it's coming here. It hits the peg, and the mass is here. And then this part, this lower section of this pendulum, actually swings up and completes a full circle. And the question is asking us for the smallest value of this d, for which this string remains taut at all times. So how can we approach this problem? Let's first think about what this question really means. It is asking us for the smallest value of d for which the string remains taut. What does that mean? Well, that means when this mass goes up at this highest point of this revolution, this mass should have enough velocity so that it completes a full circle and it wouldn't fall down or collapse midway. And so now our job is to find what is the smallest value of d so that it produces a value of velocity v, so that this mass is able to complete a full circle. And to find this, to relate v with d, we can use conservation of energy. And let me just reword this one more time. We're trying to find the smallest d such that using conservation of energy, when we calculate and get an expression with d inside it, we're trying to find the smallest of d such that that expression yields a velocity v that enables this mass to complete a full circle. And so let's try to do that. Let's first, step one, find the minimum velocity needed to complete a full circle. So here, let's try to use the conservation of energy here, since there are no external forces, since there are no other forces and there are no friction. So let's try to do that. Let's imagine when the mass is actually here at the highest point. Let's look at the initial energy. What is the initial energy? Well, we know that the initial energy, there's no kinetic energy since this mass starts at rest. And for potential energy, the height of it to the ground, let's call ground or the 0 point to be the height when this mass is at its lowest point. Let's call that to be 0. Then this height is just L. So that initial potential energy is just mgl. Just add a 0 here to indicate initial. And later, when it's here, there is a kinetic energy, half mv squared, and a potential energy, mgh. Let's try to derive h here, and let's try to do some geometry. So if we look at this diagram, we're trying to find this distance. Apologies. We're trying to find this distance, the highest point to the ground. So how can we do that? Well, we know that when this sphere goes around it, it goes in a circle. And so then this distance must be equal to this distance. Let's call that y. And we can get this y easily, since we know that this is L and this here is d. And so this y here, this should be L minus d. So this bigger chunk minus the smaller one, we get this distance here. And since it's a circle, this segment must be y too, which is also L minus d. And so then we know that height is just 2y, which is 2L minus d. And so then let's equate these equations. We know that mgl equals to half mv squared plus 2mg L minus d. And there, now we have this expression for the energy. We just now need to find v squared. What is the minimum value of v such that the string remains taut. And in other words, such that this mass completes a revolution. So let's go back to the basics here. We know that when this sphere is at its highest point, and imagine if that is the peg here, what forces acts upon it? Well, we have gravity, and we have tension. And these two forces, when added together, provide the centripetal force needed to complete this revolution. And so then the minimum velocity must be when this tension is 0. Right? Since we don't want any more, since the higher the centripetal force, the higher the velocity. And so we want velocity to be as small as possible, so we should provide as little as centripetal force as possible. And so we should let this tension to be 0. And so that is the minimum we can get. So then mg equals to mv squared over r. And what is r? Well, r is just this y. And for y, we said that y is L minus d. So mg must be equal to mv squared over L minus d. And so then v squared equals to g L minus d, since m cancels. And so the v minimum is just square root g L minus d. And so then plugging this into the equation, what do we get? So we had mgl equals to half mv squared plus mg L minus d, and a 2 here. And we said v minimum is g L minus d. And so if we plug that expression back in here, we know that mgl equals to half mg L minus d plus 2 mg L minus d. And so then from there, what we can do is rearrange this equation to get d on one side and L on the other side. So mgl, let me just cancel out all mg here. So we have L equals to half L minus half d plus 2L minus 2d. And so if we move this expression to here, we get, and the d terms to this side, we get half plus 2d, which is 5 over 2d equals to, so this side becomes 3 over 2L. And so then d equals to 3 over 5L. And so that is the minimum value of d when v is the minimum. And so this is our answer to exercise 5.40. Thank you for watching.